Okay, so today we're gonna finish off the exam review for exam 3. So we're gonna start off with nomenclature, since this is the part where we all save to the last, right? So then let's start with the acid chloride. So this is the hardest thing for me. What you're gonna do first is you're going to number your longest chain, as you always do, and you're gonna start from the carbonyl. So 1, 2, 3, 4. So then I know I should have butane in the mix, right? And then I have a substituent and carbon number 2, so 2-methyl. That's another piece of our puzzle. And how you're basically going to be doing acid chlorides is you think of them as carboxylic acids. So the ending for carboxylic acids, or like naming carboxylic acids, is ic acid. But if you're doing acid chlorides, it's going to be, the suffix is going to be ol chloride, ol chloride. Sure. So then for this one, of course, we name our substituent first, 2-methyl. So our only substituent, so we can start naming the parent. So 2-methyl butane. And usually if this was a benzoic carboxylic acid, we would put butanoic acid, butanoic acid. But instead of the ic part, I'm going to add this. So it's 2-methyl butanoyl chloride. Let me check myself. Yeah, that's good. Cool. This next one is for amides. So for the amides, what you're going to do first is name the substituents that are on the nitrogen. So you're going to start, we have an ethyl group right here and a methyl group. So you're going to do on my nitrogen, N, I have an ethyl. And I'm putting ethyl first because in the alphabet, E goes before M. So N-ethyl, N-methyl, because that's also on my nitrogen. And then you name the parent. So the parent for this one is benzoamide. What benzoamide looks like. And so just because you have the substituents, you're adding them in the beginning, but it'll be N-ethyl, N-methyl benzoamide. Let me check myself. Look, we're good. Okay, next one is for esters. So esters, you're going to name the substituent on your oxygen first. So we have a methyl group. And I believe that's the first thing that's going to be on your naming. So you name the substituent on the oxygen first, and you end it with eel, right? And so from there on, you name the rest of the compound as normal. So I'm going to start off again with the carbonyl carbon as number 1, and I number my longest chain. And my longest chain is a butane. But I also have 2 substituents coming off of my butane that are the same. They're 2 methyl groups. So I'm going to put 2, 2 dimethyl. Methyl, 2, 2 dimethyl butane. And so this one's going to be like the oic again. So instead of the ic acid, you can put 8. So methyl 2, 2 dimethyl. Yeah, methyl 2, 2 dimethyl. Ooh. Wow. Okay. Butane Oh, wait. Let me resize this. Remove it. There we go. And that'll be the name for this one. Cool. There's a couple of other ones that you should know. So it's the acid chlorides, the anhydrides, esters, and the amides. But you should also know how to do the beta lactams and beta lactones. So those are some of the important ones. And I guess I can go over beta lactam and beta lactone, because these could probably be in your exam. So for this one, okay, let me just give you the two different ones. For this one, we have an amide, and this one we have a ketone, or an ester group, right? But the reason that I put the amide is so that you can tell the difference between lactams, lactam, and lactones. So you're going to clearly see that the own part is going to give you the ketone, and we're not going to be talking about this amide structure. And then how you name it is you start off with the alpha carbon. So alpha, you go down, so 2 carbons away from my carbonyl carbon is beta. And then you keep going from there. So you kind of have to know a little bit more with the Greek alphabet. So you know alpha, beta, I believe this is gamma. I don't know, but I know this is a symbol for it. So then if I'm supposed to name this one, I put the symbol for it, and I put lactone. If I'm going to name this one, I do the same thing. I start with the alpha carbon, I go to the beta until all of a sudden I hit the nitrogen. So this one is going to be a beta lactam. And what's the difference between these two? You got the ketone and the amide. Okay. I'll leave that there, and we'll concentrate on this next question. Arrange the following protons in order of increasing acidity, from 1 being the least acidic to 4 being the most. For this one, you need to know your pKs. So for, let me see. I guess the important ones, especially for this chapter, since we're talking about alpha and beta carbons, you need to know the difference between these two alpha carbons and their pKas. So the pKa in the middle of these two carbonyls is going to be lower than the pKa of this one. Reason being because if you were to draw the conjugate base, which is, just imagine that I took this hydrogen off, you would get this as your new structure, as your conjugate base. Yeah. And so your conjugate base is able to resonate 2 ways. So this additional resonance is stabilizing it. And then we know that the stable conjugate base equals a more acidic acid. So that just like gives an explanation to why the pKa for this one is going to be 9, and the pKa for this one will be 19, because this one will only be able to resonate 1 way. Okay. For the next ones, these are just the ones that you should know. So for the acetic acid, which is this one right here, my proton here has a pKa of 4.8, whereas my benzoic acid has a pKa of 4.2. Reason being, again, because we have additional resonance structures right here, whereas over here we only have 1 resonance. Something to stabilize my resonance only 1 time, whereas over here you have a ring to stabilize. Yes. So it's all about the stability of the conjugate base and the acidity of your acid. So that's like the relationship. Okay. For number 3, devise a reasonable synthesis for the following. So this one, I would want you guys to try this out by yourselves, so like pause the video and then do it. This one's a little bit harder. I just wanted to do this just to introduce or to reintroduce you to some of the reagents that we use in OChem 1, which you could be using in either your test as a final exam or like in this test when they give you a synthesis problem. So for this one, what I did is I used PCC to make this alcohol a carbonyl. That was my first step. The second step I used was I did an organometallic. So there you go. And so our organometallic attacks the carbonyl carbon, and we add it onto our compound. For the third step, I use H2O. So whenever you form the negatively charged oxygen, you can do one of two things. You've seen it before in like enolates, but usually what you have been doing is protonating it. So what you use to protonate is just like water. And I keep forgetting that I have a hydrogen here. So then you have step number 4. And for step number 4, I did PCC, and it looks a little weird. Like, how am I able to do PCC if I have 4 bonds to my carbon? Well, one of the bonds is a carbon-hydrogen bond. So with PCC, it's an oxidative agent. So then we're going to get rid of that carbon-hydrogen bond to make another carbon-oxygen bond. So then I'm going to make this right here. I've run out of space, so I'm going to write on this side. So for step number 5, I used LDA, THF, and negative 78 degrees Celsius to indicate that I'm doing kinetic, right? Okay. Let me get this out of the way. Oh yeah, so LDA. And LDA, it's a big bulky base. You should also know the structure of LDA. So lithium diisopropyl amide, which just looks like this. So amide, so we have a nitrogen. It's diisopropyl, so then we have 2 isopropyl groups. And lithium is in front to stabilize the charge. So know the structure for LDA. Okay, for 5th step, LDA is kinetic, so then we're going to deprotonate the alpha hydrogen on the left side to make it an enolate. And for step number 6, I did just an acid chloride, but there is another way that you could do it. So you figure out another way to do it, let me know and I can check if you got it. I had 1, 2. Yeah, and that will be this group right here. So hopefully you're reminded that we have like PCC that we can handle, and you can do your organometallics too. There's lots of things you could have done with this one. You could have done like a Friedel-Crafts kind of reaction. Anything you can do to form that reaction doesn't have to be what you've learned in this chapter, but that's like what they're trying to make you do. If you know another way to do it, just do it. Okay, this next one, which monomers could be used to form the following polymers? Okay, so here we have 2 different polymers. Let me get this out of the way. Which monomers can be used to form the following polymers? We have 2 polymers. On the top one, we have a polyester. So notice how we have lots of ester groups. Poly means, I think it's more than 3, so more than 3 esters in your compound. And in order to make polyester, what you need is a diacid and a diol. Diol means a compound with 2 alcohol groups, and diacid means what is it called? A compound with two either acid chlorides, or which in this case is what we're using, acid chlorides, or carboxylic acids. So then that's the first one that we'll be dealing with. And I guess we could just do this one for now. So the way that I used to do it, because it looks really confusing, like where should I start and stop my monomer? What I do is I find my carbonyls, and I know that I'm using a diacid, and usually for these you use acid chlorides. So what I do is I cut it off right here, because when you're using a reaction like this, when we're doing a reaction like this, what usually happens is you substitute the acid chloride for, the chlorine for the OH group, right? So that's basically what we're going to be doing here. We're going to cut off the right and the left side of the carbonyls. So you should have two carbonyls in your compound since we're going to have a diacid. And I'm going to do that for every one that I see just to make it clear to me. It's going to be cut off. Yeah, so all of this compound should be one thing. All this compound should be one thing. Cool. And notice how the rest of it is two O groups. So we should have a diol. So this could totally be our diol right here. Cool. And then again, we're using acid chlorides. So then I'm going to do my diacid. It's two acid chlorides. So these are the two monomers that you're going to use in order to make the polymer at the top. Cool. This next one that we're doing is a polyamide. And the way that you make those is also diacid chloride and diamine. So diamine, two amines, diacid chloride, two acid chlorides. Here you're going to do the same thing. You find your two carbonyls, box them in. Find your two carbonyls, box them in. Two carbonyls, box them in. So this should be my acid chloride. Since it's a diacid chloride, I should have two acid chlorides in my compound. That's why I boxed in those two carbonyl groups. So this will be one of my monomers. So monomers make up polymers, right? And then the other one, we're looking for a diamide. We just box in the rest. So this will be my diamide. I have a total of 3 carbons in the middle of my groups. So I have 1, 2, 3, 4. And then we know that nitrogen likes to have 3 bonds to it. So I'm going to put 2 hydrogens at each end. And these should be the 2 monomers that we need to use in order to build that polymer. Next, we're going to do some reactions. Okay. For this one, they're telling you that we have iodine in excess. And so what this kind of reaction is going to do is it's going to add as many iodines as it can to the alpha carbon. So then if it's in excess and I have a total of 3 hydrogen bonds here, I can get rid of these 3 hydrogen bonds and make them all iodines. Iodines. Sure. Okay. So this makes it a good leading group. So then we have the OH, which we know is negatively charged. So what the OH will do is, as usual, we have an nucleophile, and we have an electrophile. So I'm going to attack my electrophile, bring it up. Reform my carbonyl and take off my, I forgot to add my OH since it attacked. Reform the carbonyl and kick off the leading group. So now I have carbon with 3 iodides, and it's negatively charged, right? Since I'm taking these electrons right here from this bond and I'm putting them on my carbon. So then this is going to act as a nucleophile or a base. So then you know that bases like to take away protons from acids. So then that's exactly what it's going to do. It's going to take away this proton from my acid right here. So what you form is a halogen. You form iodoform. And you also form what is it called? I forgot what the name of them are, but negatively charged oxygen. I forgot what the name of it is. I'm so bad at nomenclature. Okay, but the main point of this, though, you should have these two. You should write down these two products when you're doing your reactions page, and know that they can use any other halogen. So like chlorine, you see, bromine instead of this iodine. And instead of your iodoform that you formed over here, you can form bromoform, you can form chloroform. Okay, let me do this next one. We have a base. We know that bases like to depronate, and we've been talking about deprotonating that alpha carbon for a long time. So then I look at this molecule right here and I notice that it doesn't have a good alpha carbon. It doesn't have a good alpha hydrogen that we can deprotonate. This one, though, has a good alpha hydrogen that we can deprotonate. So that's exactly what I'm going to do. I'm going to deprotonate this and make my enolate. Okay, cool. And so this is a Michael reaction, because what we're going to be doing, or what we did, was we formed a enolate, and we have a Michael acceptor right here. And so what this will do is we're going to reform the carbonyl. This nucleophilic carbon is going to come in and attack my carbon double bond. We're going to resonate this upward. Resonate this upward. So then I like to count my carbons because this is like one of the most confusing things that I can get tripped up on. So 1, 5, 6, a total of 6 carbons. 1, 2. Okay, carbon number 2, I have a new, or I have a ketone carbonyl group. 2, 4, 6. H. Okay, cool. And I have an enolate. And so from here, I know you don't need to know the mechanism for this, and you can kind of already tell what the answer is, but I'm going to show you the rest of the mechanism. So we also have the conjugate acid right here, and so what I'm going to do is I'm going to deprotonate that conjugate acid with this little enolate that I formed. So you can either do it in the form for like when you do like an enol, or you can do it how I'm going to do it just to make it simpler for myself. I'm going to make this carbon, grab my hydrogen, break it off, and reform my carbonyl, just so that I don't have to do any tautomerization. Let's see if this works. Yeah, it should work. On the count, make sure I'm good. Oh, I'm good, and this will be my answer. Yeah. You can also, like, if you're on a reactions page, you really don't want to do all this mechanism or anything. So what I would do is, you know that your alpha carbon has to be your nucleophile, and that at one point we're going to attack, it's a 1 for addition. So we're going to attack the 4th position right here. Let me write that down, 1, 4. So then what I would do is I would do 1, 2, 3, I would number it. And I know that at carbon 3, where I form my nucleophile, I should attack this one right here. This one here. So I'm going to name this 4. And from onwards, every other carbon, 5, 6, right? So I know I'm going to have a total of 6 carbons in my compound, my final compound. 1, 2, 3, 4, 5, 6. Hydrogen right here. And I know on carbon 6, I'll have a carbonyl, and carbon 2, I'll have a carbonyl. And that's pretty much all you need to do. There's like tricks to like know how to not go through mechanisms and do your enolate reactions, because it is difficult, but it's possible to do it really quick. And you want to do it really quick if you're doing your exam. Okay, cool. Okay, this next one, LDA, THF, and negative 78 degrees Celsius. So the first thing I'm going to do is, because this was on my, they asked me to do this on my exam, so they asked me to name my alpha carbons and if they're thermodynamic or kinetic. So thermodynamic, we know that it's going to be the most substituted. So if I form my enolate here, right here, I have my enolate right there, it'll be the most substituted enolate that I can form. So then we are more stable than your other counterparts, right? So then this is when you're thermodynamic. If I formed it right here though, this isn't your most stable enolate that you can form. So then you would name this kinetic, because this would be like the first hydrogen that you see, it'll just pluck off instead of going through the trouble of going through steric hindrance in order to make a more stable one, right? So then this is my kinetic carbon hydrogen bond. And so I look at my reagents now and I'm doing LDA and THF and negative 78 degrees Celsius. So when you think of thermodynamic, you think of heat, thermo heat. And so you look at your reagents again and you see at this very cold temperature. You know that thermo heat and cold doesn't really match up, right? So then when you see the cold temperature, you should think kinetic. So then for the first reagent reaction, right? What I'm going to do is I'm going to form the kinetic enolate. For the second reaction, this one's a little bit more trickier. I'm going to form it like that. Okay. I would number my carbons again because this one could be very confusing. So I know that a nucleophile would want to attack the less sterically hindered carbon on this epoxide, right? Which would be this carbon right here, just because it has a lot less substituents than the carbon on the right. And so we know I'm going to attack this one first with my nucleophile, and we know that this one's my nucleophile right here. So I'm going to number my nucleophile or my alpha hydrogen or alpha carbon as number 1. And the reaction will happen between number 1 and the less sterically hindered carbon. So then this will be 2. And then from there on, I'm going to number everything 3 and 4, right? So all other carbons, 3 and 4. So then I'm going to write my skeleton, all my carbon hydrogen bonds that stay the same. Oh, and I forgot to draw my arrows. So this would go down to reform the ketone. My nucleophile would come in and attack my electrophile. And you can't have 5 bonds on a carbon, so then you break this open and it'll go to the right. So then again, we reformed the carbonyl. We made a new bond. I'm going to do random amounts and then I'm going to count. So this one was number 1, 2, 3, and 4. And that's good. Yeah. And I know that on carbon number 3, I have a negatively charged oxygen. Yeah. So that's good. Number 2 for the second step. Now I'll do the third step, which is just protonation. So they're using water to protonate your negatively charged oxygen. So then do everything the same. You get an OH group. Cool. The next one it's not too bad. So you should go through the mechanism of how to do this. But all this does is add a bromine. It's monosubstitution at the alpha carbon. So monosubstitution means 1 substitution at the alpha carbon. So I'm going to keep all my carbon hydrogen bonds as is. And we only have 1 alpha carbon. We have 2 alpha carbons. But on only 1 of those carbons do I have a carbon hydrogen bond. So on the right carbon is where I have the carbon hydrogen bond. So that's where I'm going to add my bromine. Then I do step 2. step 2 is an elimination reaction. They don't show you the mechanism for this one either. So I don't think this one's one that you have to know for your test. For the life of me, like I tried to find a mechanism. I think it's just a regular elimination reaction. So I do my elimination reaction and I get an alpha beta unsaturated compound. And this is not something you're, oh, it is something you're always going to get when you have a reaction with these 2 consecutive sequences. And I don't think they're going to give you, never mind, I'm not even going to say it. Okay, so this next one. The next one looks intimidating, but take it step by step and it's not intimidating at all. We've seen this all before. So first step, they're giving you a base. So the first thing that you do is deprotonate. And your most acidic carbon is the alpha carbon that is between 2 ketones, providing resonance stability and therefore making your carbon-hydrogen bond very acidic. So I'm not going to form my enolate here just because I find it easier to see it when I just put my carbon ion. Step number 2 is a substitution reaction. So let me show you what that looks like. Adding a total of 3 carbons. So from this carbon ion, I attack my electrophile and the leaving group leaves. Awesome. And I'm adding, again, this is one of the ones that you can get confused with. Remember how many carbons you're adding. You're adding a total of 1, 2, 3 carbons. So I'm gonna add a total of 1, 2, 3 carbons. And I do step number 3, which is deprotonation again. And once again, you have an alpha carbon hydrogen bond that's available. So deprotonate. Just gonna abbreviate. One, two, three, carbon ion. And I'll do step number 4, which is another substitution reaction. And I believe for this one, I meant to do a correction. So I'm gonna do it like this. Boom, 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 like this. Okay. So same thing, it's a substitution reaction. Bromine, benzene. Cool. So my nucleophile attacks my electrophile and the leaving group leaves. I'm adding a total of 7 carbons. So then make sure that when you're writing your product, you get a total of 7 carbons. Because if you mess one carbon up, you get the whole thing wrong. Boom, 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 boom. Cool. Step number 5 is H3O+. And so for H3O+, we should know that we are going to be creating carboxylic acids. All esters convert. I don't know if you guys can see that. That's the answer for that one. All esters convert to carboxylic acids. Then on my compound, I have 2 ester groups. Those 2 ester groups are going to turn into carboxylic acids. Total of 3 carbons in the middle. Okay. 6 is heat. So the delta sign that you usually see is heat. And so what the heat will do is it'll decarboxylate. Only 1 carboxylic acid. And so when I think of decarboxylation, I think of losing CO2. What CO2 looks like is carbon double bond to oxygen, or double bonded to another oxygen. And so I'm losing a total of 2 oxygens and a carbon. Same thing with this one. So notice how on my group right here, I have 1 carbon, 2 oxygens right here. what's going to happen is I'm going to take, when I'm decarboxylating, I'm going to take this whole group off, and I'm going to be left off with everything else. So what it'll look like is this right here. I have carboxylic acid group and a total of, what is my alpha carbon? 2, 3, 4. One is my alpha carbon. 2, 3, 4. On my alpha carbon again, I have, oh my gosh, did I miss a group? Oh, right here I missed a group. It's a carbon. I had to draw that small. Okay, but on my alpha carbon, I have 1 carbon coming off and benzene. There. That should be your answer. I'm going to check myself to see if I'm good because that was a lot of steps. Yeah, we're good. Cool. So this one looks like a lot of steps, but just do it step by step. And if you know what to do, like with the bases, you always deprotonate the alpha carbon, then I think you'll be good. And these are, I guess, some of the newer things that you learned. So if you keep that in mind as well, you'll get the hang of this. So this is a Malonic ester synthesis. This is one of the problems that I got on my test. So provide the mechanism for the decarboxylation step. Okay, so then we're going to do the same thing as we did previously. So I see decarboxylation. I think of losing CO2. So then on the past one, I lost a whole carboxylic acid molecule. So then here, this is what we're going to be losing. This carbon right here and 2 oxygens is what we're going to be losing. So it's going to be completely taken off. And the only thing that we should have is this. So even if you don't know the mechanism, think of decarboxylation, take off that carbon and those 2 oxygens, and you should be good. This is the product. That's at least 4 points on your test. But the decarboxylation step isn't too bad. So then if you watch this video, I'm sure you'll get a clue of what to do with if you got this question on your exam. So it's pretty much, you're gonna make an enol. So how I'm gonna make an enol is this. I'm gonna act like this is my base. I'm gonna deprotonate, right? So when I deprotonate, I'm gonna put all these electrons into this carbon oxygen bond. So now it's gonna look a little bit more like a C double bond, carbon double bond, oxygen double bond, oxygen, or CO2. So then when I do that, we know that we can't have 5 bonds to this carbon right here. So then what I'm going to do is I'm going to break this bond and create a double bond between my carbonyl carbon and the alpha carbon. When I do that, I make an enol. And that's what it looks like. I'm sorry, this should go from the bond to this hydrogen. And that's how you make the enol. So then you lost CO2. And then the final step, which will just lead me to this right here, is you tautomerize. So this double bond is going to come in and steal my hydrogen. This hydrogen bond with 2 electrons in it will make another bond between carbon and oxygen, therefore regenerating my carbonyl bond and kicking off the oxygen in this whole decarboxylation step. Cool. So again, if you have other suggestions on what to do with the synthesis, let me know. If you have other questions about your exam 3, let me know, and I can also probably make a video before your exam. But this is all for part 2 review, and I will see you guys later. Good luck on your exam.